Okay, so hi everybody. Welcome to the last One World Mind seminar of the spring 2023 semester. It's our pleasure today to have Professor Ren from Columbia. So Professor Ren, he received his PhD from Columbia in 2006. Since then, he's held positions at the University of Chicago and at UT Austin, and now he's back at Columbia. So we're really happy that he's going to be able to give this talk today on weighted least squares optimization for inverse data matching. So it's all yours.
Thank you. Thank you very much for the kind invitation to talk here. I'm not a real data science person, but I work on inverse problems. So a lot of times we do computational inversion, and that's where you really fit data to models. So from that perspective, we're doing a lot of problems that are probably interesting to data scientists. So what I'm going to talk about is something that is, I think it's completely trivial, but I keep seeing people doing this in different areas. So this is the motivation to really, re-look at it. And also, there are something that I think that is unique to this approach that has not been, pointed out, I would say. So I want to essentially highlight a little bit on that. So this is I'm going to talk about really, just give you a very quick overview of a lot of things. So it's joint work with many people that are listed here. Wending just graduated. Bjornquist is from UT Austin, and Yunan Yang will be an assistant professor at Cornell. Lu Zhang will be assistant professor at Rice. So I'll really just motivate the problem and just try to explain what what you can see in a very simplified setup where you want to fit linear models, and then try to talk about applications. So the idea is to fit data. So I worked in inverse problems, so all the setup in the inverse problem setup. So basically, you have a nonlinear model, which could be solution to the PDE, and you have M, which is the unknown, could be the coefficient function in the PDE, and G is the data. They say again, the part of the information on the solution that you measure. And you try to look at this model. The goal is to fit the data by tuning your parameter M. So this abstract model has a lot of applications. I mentioned, inverse problems, which in most of the PD inverse problems, you can look at it that way. But another very naive problem is neural network models of fitting data. So the traditional ways, again, if you work in inverse problems, you know that in most cases, for at least most problems we care about, there's not analytic solutions. Most problems are highly nonlinear, and we don't have good characterization of this map F. So what you do numerically is very often just do a least square. So you just do this least square with some, let's say, regularization, and the regularization will be different for different applications. But I just put something here just to say you can put the regularization there. So if your problem is linear, of course, you just can write down the pseudo inverse of this, and you get what you see here. if it's nonlinear, there are a lot of issues about convexity of the problem. In most cases, your F is nonlinear, so it's not a convex problem. It's very complicated, and that's a different issue. There are a lot of people trying to address that. So what I want to look at is a very slight reformulation of this problem. So instead of having the original, Fm equals G, I want to just rewrite it a little bit. So what I do is I apply some operator F tilde to both sides, and then I do a change of variable to the M. So for instance, here I say I just change M to M tilde by introduce this P tilde operator. Okay, so I just try to do that, and you can see, of course, this is a classical way of introducing, for instance, prior information on M. So this P is really there to take care of, again, whatever information you have on the unknown. And this F tilde, there are many, motivations. One is to say if F tilde is F inverse, then I solved the problem, right? But, you can try to introduce a F tilde there to change the problem. So after I change this problem, I can again solve the problem in a least square formulation, like what you see before. This is completely not necessary to do. I mean, you don't have to do it this way, but let's say I still want to do that. The reason you will see later is that there are many different ways of solving problems that are essentially in this form. That's why I write it in this manner. So there are some general comments here. The one is that, when you take, so this F tilde here is what I introduced. So if you want to keep your original solution of the original problem, they say you have a unique solution of the original problem, you take F tilde to be invertible. P tilde I have already assumed to be invertible. The other is that there's a naive case where if you take F tilde to be F inverse, which you cannot do, of course, but if you indeed can do that, you solve the problem. So you see that there's a motivation there to introduce this F tilde, right? If I take F tilde to be an approximation to F, then I essentially solve the problem. So usually you take this F tilde, I mean, depend on where you're from, but there are many cases in solving inverse problems where you take F tilde there to precondition the problem. In other words, I want to take this F tilde so that the landscape of this guy, this new least square problem is better than the previous one. Okay, so you can add the regularization. I don't want to put it here, but you can add the regularization as usual. Okay, so there are a lot of, again, I mentioned this in the abstract framework, but there are many cases where you actually have this kind of what I call weighted problem. So that operator F tilde can be, in the linear case, can be solved as a weight. For instance, I give you one example where you see that there are cases where people try to, instead of minimizing the L2 difference, they minimize, let's say, the H1 semi-norm of the residual. In that case, you can think of that as, by definition, that's the gradient of this, right? So you can think of this as a weighted least square with a weight, which is the, in this particular case, is a gradient operator. But this is just an example here. I'm saying here that there are many problems in the literature where you do this kind of minimization, but in forms that are not in what I just expressed. For instance, I list here, there are minimization with Wasserstein matrix, their minimization with this subleft training, subleft acceleration, where again you do you train your networks with, instead of L2, loss function, you can take essentially H1 loss function. There's also this many other problems that again are not in the form that I mentioned, but are essentially the same. So there are a lot of theory in the past. People in different field has look at this problem. Depend on where you're from, it looks like people just independently did a lot of things. So I mentioned a few work here. I'm pretty sure some of you in audience, so this is Willing's work, but I'm pretty sure many others have done this. So sorry if I miss yours. I mean, this, not a complete list of literature. So I want to, again, just first highlight a little bit that, doing this there are some impact there, in the sense that if I change the original problem, so take this linear problem, if I just change this problem like what I said, so because it's linear problem, now I just have this A tilde, which is the F tilde before in the nonlinear setup. This B is a P operator. So if I change this and I change the square here, I want to show you that there's impact. That is, this optimization problem is different from the previous one, even though the global minimizer could be the same. Again, when I say global minimizer, I assume there's a unique one. So all the operators are invertible, et cetera, et cetera. But even though the global optimizers could be the same, this operator A tilde here could have an impact on the solution when you have noise in your data. So I just list here example here. Example by example, I mean a particular A tilde. So if you have this M equals G, you change this problem by multiplying both sides, or apply both sides by this operator here, which is take S to be, 1, for instance, or 2. You apply Laplace to both sides. Okay, so here I just apply a fractional thing, not necessarily fractional, but just this A tilde here, that to the both side. So for that problem, I didn't change M. I didn't do the prior information yet, but I just want to take this this operator to both sides and solve the least square problem, just to say that there's some impact there. So if you look at this, so here this operator, if you want to define it formally, it's really you can define it using Fourier transform so that you have this operator defined for S. Okay, so you just take the Fourier transform, and this is the standard stuff I'm not going to spend a lot of time on. And let's assume for simplicity that A is diagonal in the Fourier domain, so that I have this property. None of this matters, okay, but let's assume that. Then if you want to solve that minimization problem, you are minimizing this least square functional here. You can write this in the Fourier domain, and then you can invert this, right? So this is, I took this example because this is closely related to a linearized version of the Wasserstein 2 matrix that people used in the inverse wave propagation problem when S is -1. So, but here this is written for any S. Okay, so why do I want to do that? Because if I make all these assumptions, you can see that the inversion, that operator put, weight operator put different weight on different frequencies, and that will have impact on the solution when you have noise. So in any case, this is simple enough. You can still linear, still convex. You can just invert it because of the assumption that A is diagonal in the Fourier domain. You can invert it in the analytically. I mean, you can write down the frequency by frequency inversion, which is this, right? Of course, this is just the original, least square solution, because you can cancel out this power 2s in the Fourier domain, right? You have this. So at the end of the day, it's canceled if everything is perfect. But before we cancel that, let me just tell you what happened here. So one of the thing here is that you see that you have your original data G, that you could have noise in it. So in this inversion that I just did, I multiplied the data by this factor zeta to the power 2s, and then I do the inversion, right? So which means that if I have noise in my data, if I take S to be, for instance, positive, I'm multiplying the high frequency part of this G by a very large number because data will be high and S is positive, okay? And then I invert this. So I amplify the high frequency part of the data, then propagate. Again, you can always say that you will cancel out this factor later, but you will see that if you have a noise, this cancellation is not obvious. So if S is negative, you are suppressing the high frequency information because G at the high frequency is multiplied by a large number. So you are essentially in the physical domain, you are essentially so this is the physical domain solution. So if S is negative, you are smoothing out your data before you backpropagate it. This is, again, a trivial calculation that everyone can see. The point here is really that there's an impact here. So smoothing out if you have a noise, smoothing out your noise and then backpropagate is certainly better than amplify your noise, differentiate your noise, right? Because if S is positive, you differentiate your noise before you backpropagate. So this is one simple calculation that says, if I want to do this, again, look at this in the Fourier framework, then taking a different type of F tilde, that weight operator, will have different impact on the solution. In the perfect world, again, you can always argue this operator will be canceled out. But I want to show you that if you, for instance, if you do this in the minimization framework, imagine you're minimizing this. In the case when you have an S that is negative or positive, let's say positive. So if you stop this minimization at a given tolerance of your objective function, right? You see here that the error at the larger frequency is minimized, while the error at the lower frequency are not as much, right? Because again, you penalize the high frequency part with this factor there. So in other words, if you stop this minimization, if you solve this minimization problem and you stop at a given accuracy, the solution has higher resolution or higher frequency content than with a S that is positive than the one with a S that's negative. Okay, that's what I want to say here. So because different frequencies are tuned differently. Okay, that's just to illustrate that indeed putting this operator there, putting this weight there has some impact. So you can make this a little more rigorous by looking at the error in this case. So what we call resolution analysis in imaging. That is, if in the setup that I just mentioned to you, you can show. Let me just skip all this. So here I just say that if you add that prior information by introducing a B matrix here, you can do the same thing. So here I just give you an example where B is also some operator like that. So I'm just saying that the M unknown that I'm trying to reconstruct or trying to solve from this match is in a H beta space. Okay, that's all what I'm doing here. So in that case, what you can show is that the best resolution you can achieve with this weighted framework is given by something like this. And this looks not understandable, but if you just take the alpha beta, take a beta to be 0, for instance, or take a S to be 0, you have the UUL2 solution. And you, with that S here, you see that if you take a S that's positive, you have better resolution because the best frequency you should cut is higher. If you take an S that's negative, because there's a negative sign here, then the cutoff frequency, the best frequency or the highest frequency you can reach compared to the previous one, okay, is compared to the L2 one is lower. So in that case, you have worse resolution. All we're saying is that, yeah, if you just do this naive, inversion like what we said here, with a positive S, you are going to have very high resolution. With a negative S, you are going to have lower resolution. That's what this particular example tells you. Okay. So that explains. So this you can see again. Is a very general phenomenon in the sense that it tells you if you really naively saying you are minimizing this left hand, right hand side with a norm that's weaker than the L2, you get worse resolution. If you solve this with a norm that is stronger than L2, you get a higher, better resolution. So in terms of convergence speed, that means when you take a stronger norm, you have locally, you have a faster convergence. So this is one of the argument in the papers that I mentioned somewhere. So one of those papers is Sobolev training basically are in that framework. But this is not the only story. That is, if you look more carefully, what I said is that when S is positive, you would have better resolution. But that better resolution has a disadvantage. That is that better resolution because you focus on higher frequency part, that make it very unstable to noise. So this is the two sides of the story that I'm trying to just illustrate in this very simple example. This is, again, completely trivial calculation there. Let me just show you some numerics. So here is one example where you take a elliptic PDE, you take the coefficient sigma here as unknown, and you suppose that you can measure, the solution of the PDE, but also times the sigma. Let's say you can measure that. So suppose that's the case. So you have a forward map like this, F that looks like F times U. U is a function of sigma. And you try to use this to recover sigma, for instance. I just want to illustrate the concept. So here are 1D simulations where you can see that if you don't have noise, so this is a very well-posed problem, very, well-conditioned problem. You don't have noise, you can get perfect reconstruction. But if you have noise, the reconstruction with the usual L2 is this blue red line. And the reconstruction with, for instance, H-1, which is weaker than L2, is this line here. So one is smoother than the other. This is where you stop at roughly the optimal, given the noise level, roughly speaking where you should stop. But if you keep pushing, of course, as you see that you will get very accurate solution as well. In this case, this is not so accurate, but you can keep pushing it to get reconstruction that looks like the red one here. But again, that is where you overfit your data model to your noise. All right, so this is in the two-dimensional case, you see the same thing. That is, unfortunately, that you probably, it's hard to see the noise in here. So this is the true one. This is the reconstruction in the L2 case. This is the reconstruction in the H-1 case. You can do a H1 reconstruction. I didn't do that, just to illustrate the fundamental idea for this nice problem. And every time you look at it like that, in that form, people always ask you, if that's all you care, can't you just do a regularization? That is, you just take the least square, you add a regularization that is, that is stronger than L2 or, weaker than L2, right? So here I'm just telling you that this is different from regularization. It's not regularization, as I emphasized from beginning. If you take your operator there to be invertible, you kept your global minimizer. You didn't regularize anything. So here is the case where I put both there. This is the weight I put there. And I also put a regularization that is not in L2 norm, but a weighted L2 norm with this just the H beta norm here. So this is actually a problem that has been, without when S is 0, this is something that has been analyzed a lot in the regularization literature. There's a recent result here to look at this problem when you have when you don't have this term, but only have the regularization term. So in this case, again, this is a linear problem. You can just find the normal equations. What you find is something like this, trivial. So this is a case where you can see clearly the difference between the weight you put in the loss function and the weight you put in the regularization term, which is this. Okay, so this regularization one is the additive operator that you introduce here, but the other one is not. This is multiplicative. Okay, so this is the main difference to the. So if you, again, this is just to say that when you put the smoothing or whatever effect you want to see in the regularization term, they don't behave the same way. Okay. So you can see here, if you take a gamma small, you can do a expansion here that give you the additive term there. So in the Fourier domain, that is much more obvious. Okay, that's the you do your so this 2s appears at your data directly, but the beta, the one you put in the regularization, does not. All right, so you can also put give a Bayesian explanation to the this weight there. Let me skip that because I want to go to a different setup. So there is actually a reason why I show you that particular linear inverse problem there, because as I said, this was a way to explain the solution behavior of Wasserstein 2 based inversion of, for instance, this the diffusion problem that I show you there. If you take a Wasserstein 2, you linearize it, the metric, which means your two signals are close to each other. Of course, they are no. I mean, they have to be positive, etc., etc. Here, I don't care about that, but if you do that in the right framework, that mimics the Wasserstein metric. All right, so here is the same example, but just in this in the machine learning framework, where you take the random Fourier model, a random particular form of random feature model. You say that my model is a superposition of Fourier modes, random superposition of Fourier modes, and you try to learn these coefficients by solving this standard linear fitting problem. By linear fitting problem, I mean that the coefficient, when you put this in the you have a parameterized form, so the bases are known. So you really have this minimization problem to solve. So this was, most of you are familiar with this, so I'm not going to talk more, but there's a study recently, this was what motivated what we look at this, where they look at the generalization error of this fitting for this random Fourier model, where you assume that your theta following certain distribution. And I said this is the same as what the model I just showed you, because the assumption here is that this theta following distribution that has a covariance that looks like this. So this sigma is the diagonal operator with k on the diagonal, 1 plus k on the diagonal. So basically, this is a case where your coefficient, if you look at the space of the functions, the models you have, those are functions that has Fourier, on average, have Fourier modes that decay in this particular manner. Okay, so this was what I showed you before when I show you that A operator is diagonal in the Fourier domain with exponent alpha. So TA just replace that exponent with theta here, gamma, sorry. So what you do is you fit your your model to the data. So you, in the paper that I just mentioned, what you do is you just change this least square problem to a weighted least square, where you introduce that P operator that I mentioned. You put a prior information on theta that you want to reconstruct. So this sigma inverse is the same as the sigma that you see there. So you just take your, sigma, you put it in a particular class where the coefficient against sigma decays. Okay, so this is what you see there. And you solve this problem. And you fit your data like this way of least weighted least square. You look at the generalization error of this fitting results. So this work here that I cited here says that if you do that, so in this particular way, which is if you just focus on your low frequency part, like what you see here with this weight matrix, then the fitting result has a better generalization error than if you just naively do it like without the weight, which is completely not surprising because your assumption is that your class, again, you see this, you have your class of function has Fourier modes that take place in this particular way. So you should look for solutions that has smaller high frequency part, let's put it that way. So this can be generalized to the following form. That is, you can, instead of just looking at this prior information on the unknown, which works well in the over-parameterized case, because in the over-parameterized case, you have your data, your W is in, you have a lot of freedom there, so you can choose the special class of coefficient you're looking for. But in the under-parameterized regime, that doesn't help. So what we did was we say you can actually put another weight here to handle the case where you are in the under-parameterized regime. So if you just, again, this is just a linear problem, you can analyze everything like what I said before, and you can show essentially what I claimed in that simple linearized problem. So there, I don't intend to show you the reconstructions, but just here to say that indeed, with that weight matrix in front, you can see that you have an impact in the under-parameterized regime, but not the over-parameterized regime. Of course, in the noisy case, it's going to play a role there also. So let me skip here. These are essentially the same thing I want to say in that linearized problem. But let me take the last couple of minutes to say one application of this understanding. I say the understanding because the theory actually, you can, if you look carefully, there are many results in the literature that tells you exactly what I just told you. So here I want to say that this very simple idea can be useful in some applications. For instance, this is an application where you have to do something like this. So this is an application where you want to say, suppose I have that model that I show you at the beginning, but I want to learn the inverse operator. Suppose I have, Fm equals G, and I want to learn the inverse operator by solving this minimization problem. So I have I can generate some data. Okay, so this is a case very different from real data science case where you have data that is from measurement or whatever that you cannot change. Here, suppose you are in a situation where you know the model, so you can generate infinite number of data. So your goal is to directly learn that inverse operator. Can you do something like this by solving this minimization problem? Suppose I parameterize my f by a neural network, where this theta denotes the neural network coefficient. So f inverse theta, this is the neural network. Can I fit a neural network that matches the data that I constructed here? Again, here, because you know the model, so you just take coefficient and you generate those data. Okay. So it turns out that there are a lot of people that have done this in the setup where you have PDE models. I listed a lot of results recently in the, for instance, full wave inversion applications, where I'm going to show you in a minute. But most of those have did not at least say anything about how stable the learning result is. So here what we said was that the operator that you had in these applications F mostly are smoothing operators, meaning that if it's a linear operator or nonlinear operator, you linearize locally, you look at the SVD, the singular values decay is crazy. So those are the operators you are inverting, which means in the inverse, there's high frequency part, small singular values are going to be amplified. So the noise in any of these are going to be amplified a lot. So in those cases, when you try to solve this minimization problem, this is a bad minimization problem to solve. And also if you match this too well, let's say you can, it's going to be very hard, but suppose you can, that's overfitting is going to kill any of the generalization capability. So in this particular case, you can argue there's a small theory you can do to say that I can actually just, instead of solving the original problem, I can solve a weighted minimization problem where I choose weight that focus on the low frequency part of the inverse operator and solve that problem to do as a surrogate model, for instance. Let me skip all this because I'm running out of time. Just to say that, just to show you some results. So this is a case where you look at the, this is a problem you don't need to care, but there's a forward model, which is a wave equation actually. You can look at, if you just forget about everything, just do a least square. So this is a problem where you have a wave equation, you have essentially a source term that is located at the center of the domain. But if you take the data and you plot the L2 objective function, your objective function looks like this. So what you can do is you do our learning like what I just mentioned. You learn a surrogate model and use that model as that F tilde that I told you. Put that F tilde here and look at this new L2 objective function. And you can compare these two to see that the second is much more convex. Of course, this is a simple problem because there's just one parameter, two-dimensional case, two parameters. It turns out that you can make this much more efficient much more powerful by looking at coefficients in Fourier domain. You cannot visualize that, but you can visualize this Fourier mode by Fourier modes. So if you just project your loss function on the first Fourier mode, second Fourier mode, etc., etc., you see how convex those new ones are compared to the old ones. Of course, when your Fourier mode is too high, it's not going to work because your training is not very accurate there. But this shows you the potential of this simple idea that can be used to construct surrogate models. So let me just skip this to say that in the last example here, I just say that there's a case where you learn so little. This is a case where you have a background plus a very concentrated object. If you do Fourier analysis, right, you look at this in Fourier domain, you have high frequency and low frequency is very little. So here you just learn the low frequency part. And then you can use that low frequency part, for instance, as an initial guess to help you to recover the whole function. So I'll stop here. Thank you.